Okay, let's get started. So can people see my screen that I'm sharing? It's the first slide of the presentation. Yes,
Yeah.
I see somebody nodding their head. Okay, thank you. Okay, so this is a pretty, the video only lasts an hour, but there's a lot in it. And so if I don't get through it all, fortunately there's a part 2 next week, and part 2 is a lot shorter than part 1. So whatever overflows from this week, it'll easily overflow into next week if we don't finish covering the whole thing. So
do we actually have a session next week, or is that a break for the holidays?
Oh, that's correct. That's correct. So it's the week after. That's right. So let me remind everybody that next week we're taking a break because it's holiday and so on. So we won't meet next week, but we'll come back the following week and continue our schedule of weekly meetings. So that's a great, thank you for reminding me of that. Are there any other announcements or things that people want to convey to the group? Yes, no? Let me see. Okay. Okay, moving to the next slide. I'm using LibreOffice Impress, and so it doesn't work the same way as PowerPoint. So the only way I can move around in the slides, it seems, is just use the slide sorter. So that's how I'm turning the page. This is a slide we saw from last week's presentation, but I'm wondering if everyone's gotten this done, and if anybody encountered any problems setting up your ability to run the notebooks. Did this go more or less smoothly for everybody, or you already had it?
I used the Colab, so I didn't bother with this. And it worked fine.
Where can we find all this, the slides?
Oh, it's in the repo, the GitHub repo. Let me go to there. And so you can get the slides and also the notebook, the modified version of the notebook. It's just slightly modified from the original, but it will be the one I'm following. So let me go there and show you where it is.
Yeah, sorry, I wasn't here last week, so I'm just catching up.
Yeah, no problem. So I have a repo that I made for the class, and it's, let's see, I think that, sorry, I'll just copy it and go into the PowerPoint and so you can see it. Let's see. Go back, slide sorter. I'll make a new slide just for now with that on it. So that's my repo, and
awesome, thank you.
Okay, great. Save that, move on to the next. Okay, so this the first 2 slides are just, again, from before, setting up your compute infrastructure. And if anybody has any problems with this, I don't want to talk about it now, but we can talk about it on the forum or on the Slack group. Just ask questions and people will help you, or I'll help you, one or the other. Okay. So, and then the second one was how to run a course notebook. Again, this is from last week's presentation. Okay, so let's start for today. So the topics covered in the class, this is a list of topics covered in the class, and yellow highlighter is the one we're going to cover today, which is called Topic Modeling with NMF and SVD. These are abbreviations, and my policy when I use abbreviation is to always expand it, at least on the first reference. So NMF means non-negative matrix factorization. And that just means we're trying to, a non-negative matrix is just a matrix that has no entries that are negative. So all the entries are either 0 or positive numbers. SVD, and so we'll get into this later. And SVD is called singular value decomposition. These are 2 techniques to factor a matrix. And we'll see why factoring a matrix is useful for us. So that's the topic for today. Those are the topics for today. back to the next. Okay, I think the first thing we need to do, and some of you will just go to sleep when I do this because you already know it cold, but not everybody does. So I thought the first thing that I want to do is review matrix multiplication. And I found this really excellent slide that that shows you how to think about matrix multiplication. And this is exactly how I think of it. But this is kind of a really ingenious slide. Let me see if I can go to full screen to make this bigger. Does anybody know how to go to full screen with, is that it? There, no? This is LibreOffice Impress. A lot of you are probably familiar with this. Does anybody know how to go to full screen?
You should be able to just go to slide and
Slide?
Yep, full screen. Go under slideshow. Next one over.
Slideshow.
Next one over. Next menu.
Next tab over. Yeah.
Slideshow. There we go. Slideshow. Start from current.
There you go.
Okay, this is good. I'll have to go in and out of this, but let's see. There we go. Okay, does everybody see it now projected nice and large?
Yeah,
Yeah.
yeah, it looks good.
You can see it. Okay, great.
Yeah.
So we have two matrices that we want to multiply, and there's a way I can annotate, so I'm gonna do that. Let's see, I think I can get this pen. So these are the two matrices that we're trying to multiply. You know, this is A, and this one is B. So we want to multiply these two matrices together and come up with the product matrix, which we call C. So the way to do it is to start at the top, and it goes, and every row in the first matrix in the product has to have the same length as a column in the second matrix for the product. And you're basically taking the product, the inner product of a row with a column. So if you want the 2 element of this, okay, so let me go over this again. A is some matrix that has n rows and p columns, where n and p are integers, right? And in order to multiply A by B, the number of rows in B has to be the same as the number of columns in A. Does that make sense? So you have to notice this, that there's P columns. Let's see, I can't erase it. There's P columns in matrix A, but there's P rows in matrix B. That has to match. And that's the only rule about the sizes of the matrices that you have to worry about. The number of columns in the first matrix has to match the number of rows in the second matrix in the column, in the problem. So what we're doing here is, pardon my bad handwriting, but we're multiplying A times B. That looks like a first grader. Okay. The product of those two matrices is equal to C. That's what we're doing here. Can people see when I annotate the slide? Yes?
Yeah.
No? Okay.
Yes.
Okay, great. So as an example, then let's compute the 2, 2. Okay, now these indices are, the indices that you see are indexing the elements of the array by their row and column. So A21 means row 2, column 1. A2P means row 2, column P, right? And ANP means the bottom row, AN, row N, and column P. That is the last row and the last column. Does that make sense to everybody? That's the indexing technique that we're using to describe the elements of these two matrices. So if we could describe all of these elements in C, so we know that C is going to be n, that's what I forgot to mention all the way. So to complete this concept that I told you, the rules for multiplying matrices, the rule is that the number of columns in the first matrix has to equal the number of rows in the second matrix. And then the second rule is that the resulting product of the two, the product C is going to have n rows and q columns. So you see, n rows, the number of rows, it has the number of rows of the first matrix and the number of columns of the second matrix. So that's how you can always tell, like if you have two matrices being multiplied together, you can check that the number of rows in the first matrix is equal to the number of columns in the second matrix. And if it's not, then you can't, sorry, I said that backwards. If two matrices A and B are being multiplied together, you have to check that the number of columns in A is equal to the number of rows in B. Otherwise, you can't multiply those matrices because it just doesn't work. So if you're writing a computer program and you're trying to multiply two matrices and you get some kind of an error, the first thing to do is to check whether those matrices are the right dimensions. Usually the error that it'll throw will tell you that the dimensions don't match right. Okay, and then the second rule is that the product matrix has the number of rows of the first matrix and the columns of the second matrix. Does that make sense? So everybody might already know this, but I think it's useful just to go through it in case there are some that are rusty on it. Some of you might have had this in a class a long, long time ago and you need a refresher. So that's what I'm doing here. Okay, so now if we could specify the CIJs, all of the CIJs, for all the n rows and q columns of the product matrix C, that's a way of specifying the matrix product. So the way to specify a random row and column, let's say the C22, the element C22, comes from the second row of A times the second row of B. That's not the best example. I'd rather have Cij. Let's see, just some random. I can't write that small though. But anyway, the point is that if you want Cij comes from the ith row of A multiplied by the jth column of B. And when I say multiply a row times a column, I mean the dot product. So it's just the sum of, so what does it mean to multiply this row together? It shows you here. Each element is multiplied together with the corresponding one. And then all of the elements are summed together, and that gives you the result. I think this is a beautiful example of a great graphic because it really shows you how to do this. And now, presumably, if I ask you for the C34 element, you would know that I have to go to the third row of A and multiply it by the fourth column of B. And similarly, you could calculate any of the elements of C, and therefore you know how to multiply two matrices together. Okay, any questions on that? Okay, great. Let's move on. Let's see now, page it down. Okay, get rid of this annotator pen and the annotation state. All right. Okay, so there's two methods of matrix multiplication, and we want to discuss both of them. The two methods are non-negative matrix factorization. That means take a non-negative matrix and factor it into the product of two non-negative matrices. There's a good discussion here, and Rachel refers to it, so I think I'm going to exit the full screen and go to this web page. I think I have it set up. Let's see. No. Yeah. Yeah, this is the one. If I get rid of this annotation. Sorry about that. I don't know how to get rid of this annotation. All right, so this is
Joseph, your annotation toolbar should have a clear annotations button.
Oh, okay. I have my pen, but there's no toolbar. I'm using the pen from Zoom, and it doesn't have a toolbar.
Oh.
Oh, there we go. Pen clear. Yeah. Oh, that should do it. Let's see. Clear. my drawings. Excellent. Thank you so much.
No
So I
problem.
have to hover over that annotate tool, and that gives me the menu. Okay. Okay, so the idea is we're going to take a matrix and factor it into two pieces. And why would we do that? Well, let's look at this, an example from what Netflix does to make use of its user ratings. So you can imagine there are millions of users and probably thousands or tens of thousands of movies. And so they build this big matrix with a row for each user and a column for each movie. And what's in the row and column, it's the rating that the user gives to the movie. And so obviously there's going to be lots of blanks because, there's 20, let's say if there's 10,000 movies and, each user has only seen, maybe dozens of them. Or if you're really a media consumer, you might see hundreds of them. But so this is a sparse matrix. There are lots of entries that are blank. And so what you want to do is be able to predict how this user would rate this movie, even though you don't know. So the way you can do this is to pull apart this matrix and try to factor it into two pieces. And two pieces such that when they multiply together, they match all of the known entries. And then the unknown entries are whatever they turn out to be, and that would be your predicted ratings. So that's what it is. The task is to predict the missing ratings. And matrixation is how we're going to do it. So let's see, I think we should go to the presentation, the notebook now, and move from there. Before I do that, the first part of the notebook, where they're importing a data set, and the data set that's being imported is news groups from scikit-learn. So we're going to be looking at, first thing we're going to be doing is we're going to be looking at the news groups data set. I'm switching topics now because I'm going to come back to matrix factorization. So you load the data. Scikit-learn is a library that you're installing here. Where is it? Here we go. sklearn. You're installing packages from sklearn, and one of them is decomposition, which we'll use to pull apart matrices to matrix factorization. And the other package you're importing is this fetch 20 news groups. So there's this data set called, I think it's just called news groups, and it's got 18,000. It's got posts from 18,000 news groups with 20 different topics, posts on 20 different topics. So we're just going to look at this. So first we fetch the news groups. We remove the headers and footers and quotes to make it. And here it looks like we're just looking for these 4 categories. We're looking for a reduced version of this so that we can play with it. Okay, so.
I have a quick question.
Yes.
No, it seems like in this notebook, and actually most of the other things I've read, is that no one makes use of no one uses training then test and uses the test to validate. It's like people just, like in this notebook, it just uses the training data and then we quickly move on. And I was just wondering, what about, using the test data to actually see how good this performs?
A good question. So when we're doing natural language processing, this is an unsupervised learning task, and that is for example, when you're trying to build a language model, what you're trying to get is given a phrase or given a set of a string of words, you want to predict the next word. This is done without a test set because your training set is the test set. You're basically using the training set as the test set. And we'll see that as we go on. But this task doesn't require a test set. These tests that we're doing right now, they don't require a test set.
He actually he does use the test set, but the point of it, or she, the point of the test.
Sorry, can you speak up, please? I'm not hearing.
Can you hear me better now?
Yes, now. Yes.
Yeah, the test set is used, but it's used only the only way it can be with a human eyeballing it. So we do use the test set to see if the related docs really are related. That's the only way.
Okay, yeah.
That's the only way you can use a test set, pretty much, in a unsupervised, right?
Yeah, it is an unsupervised task. So, okay, so we're getting the data, and the data is just newsgroup posts. That's what all this is. And then, so we just have each entry is a newsgroup post, and we're only looking for 4 of the topics. And we're only looking for, what did we say? 4 of the topics. And so it turns out that of all the posts in there, we only had 2,034 that had all these 4 topics had any of these 4 topics in them. So,
so we're trying to predict the topic of the article with this data set. Is that right? So like,
yeah, that's what this.
And then the target or the label is what article, sorry, the category of the article. Is that right?
Well, right now, all we're trying to do is demonstrate stemming and lemmatization. That's what we're doing with this data set for this part of the folder, so this part of the notebook. So let's just bear with, and we'll get to the model, what the model is, and so on a little bit later. Okay, so we're just downloading this now for the purpose of looking at the meaning of this stop words, stemming, and lemmatization. So stop words are just very common words that, and they didn't use to track them like a lot of natural language processing. They just used to ignore them because they maybe had limited processing power, and they didn't want to spend the processing power to include all of those words, because you could cut down your problem by quite a lot by eliminating the very common words like the and a and all that. But more recently, we have tremendous amount of processing power, so we're not limited by that anymore. Hold on for a second. I have to close my door. Okay, back. Okay, so so Rachel makes a point that we don't usually remove stop words anymore. But here is a list of stop words as gotten by this sklearn feature extraction. And they're words that are very common, as you see here. And so a lot of times when you process text, when you eliminate, basically just eliminate all the stop words, so that processed text would look really strange to somebody trying to a human that was trying to read it. Okay, what is stemming and lemmatization? That is a way of getting a root of the word. And what Rachel says is that she quotes, stemming is the poor man's lemmatization. Lemmatization is the sort of the principled way to get, it uses language knowledge to get the root word. So so here you have a list of a bunch of words, and here you might say that the stem word is organ or organize maybe. It basically traces back using knowledge of the language to the root word of a word, and it replaces that word with its root word. And again, democracy, democratic, and democratization probably would have a root word of democracy. Stemming is the poor man's lemmatization because it's much quicker. It doesn't require a lot of processing. It basically just chops off the last part of a word. So it might chop off the ization. It might chop off the ic, the IC from democratic. And so it doesn't get as a quality result like stemming does. But if you don't have a lot of processing power available, it's the best approach. So So let's see, we talked about this news groups data set. Now we're going to switch to this WordNet data set. WordNet is, I went to the website, it's from Princeton, and this is the quote that describes what it is. It's a large lexical database of English, and it knows about nouns, it knows about adjectives, it knows about adverbs, and so on. And then to process this, we're going to use this toolkit called the NLTK, the Natural Language Toolkit. So you have to import it. I think that's all you have to do is import it to be able to use it. And we're using it because it has stemming and lemmatization tools. So we download it, we use its stem function, and you can then, so then I guess Rachel made a list and then asked it to lemmatize, and it takes each word and maps it to the root word. And you can see it mapped feet into foot, foot into foot, foots into foot, footing into footing. So that's the best it could do as far as tracing it to root words. But if you stem the word, then it doesn't really do anything but chop off the end. Okay, so in this case, it got a similar result, but you can imagine cases where the results would be quite different from just chopping off the endings. Rachel also introduces us to Spacy, another natural language toolkit, and it calls itself Industrial Natural Language Processing, which is a big claim, but it's pretty cool. And here's the website. And Spacy doesn't even use stemming. It just thinks that stemming is such poor quality compared to lemmatization that it only uses lemmatization. So remember the difference. Stemming is just chopping off the ends of words, whereas lemmatization is actually tracing each word back to its root. All right, so she describes how to install this because it's not in the FastAI library. You have to actually install it. So it's easy to do that. And once you've installed it, you have to download the English language model. And it has a couple of different language models. This one is the small one, and then it has large ones too, which are much more unwieldy to deal with, so they have much more words. Okay, so then how you use it, you import it to lemmatizer. You then do the same thing, apply the lemmatizer to this word, to this list, and out comes the processed lemmatizer list, which is essentially the same as we got from NLTK. There are some slight differences, and I think that she has as an exercise, what stop words are in Spacy but not in sklearn, and what stop words are in sklearn but not Spacy. And I filled in the blanks here, but you could ignore what I did and do it yourself. Let's see. And then the later, more modern approach is that stemming, punctuation, stop word removal, lowercasing will hurt you in real world applications. So it gets you speed, and it gets you, because it chops down your text that you have to deal with, but it loses you information about context and so on. And so now when we have neural networks and much more processing power available, the new approach is we don't do these things because it loses information. Okay, let's see, data processing. Okay, so then, yes.
Has anybody worked with R for natural language processing? And just wondered if
the R language tools?
The R language?
I haven't. I'm familiar with R, but it's not, I don't usually use it.
No worries, just a thought.
But they have good, I'm sure they have good tools over there to do the same kind of tasks.
Not that I can see. Go ahead.
Pardon?
If I have a question. So if stemming is not useful anymore, then why are we using it for this example because it's a pretty simple example? It's not a deep neural network we're using.
I think the reason why she's introducing is that this is kind of like a historical introduction to natural language processing, which is, they've been developing this field for decades, and but over the last year and a half or so, it's undergone a tremendous revolution. And so this is still sort of these classic tools. I mean, Spacy is more modern and people still use it, but maybe NLTK is an old tool that it doesn't get used that much anymore.
Yeah.
Yeah, so I think the reason why she's introducing this stuff is just historical, so that if you take a class in natural language processing and you don't know some of the historical facts about it, then you know, maybe somebody will say, well, you didn't really learn the subject thoroughly. I don't know.
Also, Spacy, I mean, there's two things to mention about Spacy. Firstly, Spacy has a pretty good course in itself. It takes like a few days to do it, but it's really actually quite good. And I think the difference with Spacy is that it's more of a production system. So the onus is on like speed, scalability, and being robust in an actual production system. Whereas like a lot of the other frameworks are more about research. So you would use Spacy if it's production critical, I think. And it's got pipelines and so on in there. So even the course goes into like how to build a pipeline to process lots of docs, for instance.
Also, stemming and lemmatization is still important unless you're doing deep learning. If you're doing all your NLP and deep learning, then it's not important. But if you're using scikit-learn or something, you're going to be using stemming and lemmatization. But if you do deep learning, that's the only area where it's not important.
Can someone talk about where you actually use this in practice?
I can. Can you hear me okay?
Yeah.
So I've been doing some LSI topic modeling, latent semantic indexing, using Gensum.
Okay.
Yeah, and
sorry, Darren, could you speak up a bit? I'm not hearing you well.
Well, let me see. I'll take my headset off and put you on speaker for a minute, okay? I guess my headset's screwed up. Sorry about that. 1 second. Now I'm fumbling around here, guys. Sorry.
An LSI. So basically, you want to index by some latent variables. Could you talk more about that too? I'm not familiar.
Yeah, I mean, isn't LSI basically another name for SVD?
Yeah, it uses SVD. I think it's a particular implementation as opposed to LDA. I just use, can you guys hear me okay?
Yes.
Okay, I don't think I could answer that, but I know LSI uses SVD, that's for sure. Right, and so whenever you do any of this topic modeling stuff, you're going to stem or lemmatize, and stemming is more lossy, but lemmatization is less lossy, less compression though. And you know, you have to do that because otherwise the matrix or the topic space, you know, won't know that the different forms of the word are the same word. So it helps you by compressing the same word, the different stemmings into a single stem. It compresses that word into, you know, all those 5, 6, 7 words into one word, and that helps the topic model then treat those as the same, and then it can identify concept space by seeing which one of those compressed terms into stems are near each other. But it's definitely part of the practice.
Well, so what I don't know is whether it actually compresses each word into its stem or whether it actually retains the information. That is, it has this word going, but it knows that the root of the word is go.
No. Yeah. I mean, the way you do it in Gensum, I think anyone who uses it, I don't know if everybody stems and lemmatizes, but it seems like it's that way in all the tutorials and documentations, and I do that. It doesn't retain any of that. Basically, I tokenize, right? Like I have all my documents.
Yeah.
I tokenize, and my tokenization includes stemming. And it also includes, I have a phrase model. So I end up with one field for each document in MongoDB that has the phrase. They're not all phrases, but it has, you know, unigrams and phrases, and they're all stemmed. And that's what goes into the Gensum LSI SVD process. It doesn't.
Okay.
It's typical. That's classic, and you still do it that way.
Okay. So you're saying that this process, the way that you do it, you actually reduce each word to its stem. In other words, you throw away the ending. You just reduce each word to its stem. Is that?
Well, I mean, I'd rather be
That-
lemmatizing. It still works. I'd rather be lemmatizing because you do lose some info, but
Yeah. But lemmatizing the
I
same
had-
thing. You're saying that lemmatizing reduces each word to its root.
yeah, which is better. But it's slow.
Um,
The package that is quicker, I couldn't get to work, so I just did what I could do.
Yeah, I think that there are. I'm going to stop my video because I think I'm losing bandwidth. I think that there are methods that actually keep the information. In other words, it keeps the word and its root so that it can use it later on. But and I think Spacy might work that way, but I'm not sure. Anyway, let's move on to because I really want to cover what I really want to cover today is the two methods of matrix multiplication sort of matrix decomposition that we have in this first lecture. So I think that the ordering should be the second one, should be the non-negative matrix factorization first. So let's cover that. Let's cover that first. What you're trying to do is you're trying to take a matrix and pull it apart into a product of two matrices that multiply together to give you the same matrix that you started with. So in this example, the matrix is an image, but it doesn't have to be an image. The point is that, and again, the point is that you don't find an exact W and H that actually reconstructs B. This method gives you an approximate reconstruction. So there's going to be an error, but I think that you just try to get as close as you can. And I think you can control that. Here we're doing V, which is this vectorized image, and we're, or actually it's a whole matrix of vectorized images. What is a vectorized image? It's when you take the matrix, an image is a 2x2 matrix, a two-dimensional matrix. If you just take that matrix and make it into a vector, a column vector, in other words, stringing all the pixels end to end, and the way you do it is you go through like columns. You tack on the first column, the second column to the end of the first column, and so on, of your image, and then you end up with a long vector. So that's what it's done. It's converted each image into a vector, and they want to, they're trying to pull apart facial features and importance of features, and so they're making the product of W and H. So W has to, so actually the dimensions would be nice to see here. Let me go back to the other example that I had in that, sorry to do this to you. I'm going to go back to this example. So we're trying to factor a matrix, and in this case, the matrix that we're factoring is the Netflix matrix, the users by movies and movie ratings matrix. So it's generally applicable, so that you should see that the example that was covered in that Rachel points to in the notebook is the same process. You're taking a matrix and factoring it into two matrices that multiply together to give you the matrix back. It's widely applicable. You can have your matrix can be vectorized images, or your matrix can be ratings. I think it's easier to think about movie ratings for us right now. So let's think about this. So R equals, we're trying to pull it apart into P times Q transpose, and what we get is an approximation to R. That's what this little caret on top means. It's not exactly, we haven't exactly reconstructed R, but we've reconstructed it an approximation to R. So in our understanding, you get to decide how many features you want to represent. So if P is, so if R is a U by D matrix, U is the number of users, and this is the absolute value brackets mean number of users, and D is the number of movies. I don't know why they use D. But if you want to pull it apart into the product of a matrix P and Q transpose, then P should be a U by K matrix, and Q should be a D by K matrix, so that its transpose would be a K by D matrix. And then when you multiply P times Q transpose, you'll have a U by D matrix. Does that make sense to everybody from our discussion about matrix multiplication? Okay, so the point is that that this part is arbitrary. The K is up to us how many features that we want to represent in our matrix decomposition. So generally, you choose a small number, like I don't know, 3 or 4 or 10 or something small. Whereas this matrix has U has millions of entries, millions of users for Netflix at least, and D probably has tens of thousands of movies for Netflix. And we want to try to the idea of this is we're going to try to identify some kind of genres or categories for these movies, and try to separate them into those categories, and also users that have affinity for those categories. So K would be something small, you know, like 4 or 5 or 10. Okay, we're trying to do that. So I don't want to go into the mathematics, but in our notebook, Rachel did this, and there's a key thing where we'll go into this as soon as I finish introducing the topic. We're going to go into the britlit.xls, where Rachel did some great examples of the matrix factorization methods that we're studying. Okay, so all you need to remember now about non-negative matrix factorization is it's a way to factor a non-negative matrix into the product of 2 non-negative matrices. And as I said, the intermediate dimension, you get to choose that. So, okay, it's up to you to choose. So the other technique, so that's the first technique. I think it's easier to think about factoring a matrix into 2 pieces than it is to factoring into 3 pieces, which is the first method, singular value decomposition, another way to factor matrix. And the way you do it here is you factor the matrix into, so A is some m by n matrix, and it's usually m is the number of rows, which is the number of examples that you have, or in Netflix it's the number of users, and n is the number of features. And so the number of features is always less than the number of users. N is the number of well, n is movies in the Netflix example. So generally, you're dealing with tall, skinny matrices. So remember that. The general process of breaking down a matrix into these special types of factors is called singular value decomposition. It's one of the most magical techniques in all of applied mathematics, and it's certainly the most important for us to understand in terms of practical application. We don't have to understand the theory behind it, but we have to understand what its practical application is. So what it is in this diagram here, which is taken from the Facebook page, is a reduced version of SVD, where we're not getting the full number of diagonal values, because normally this would be an m by m matrix. The purple matrix would be m by m, and R would be also m by m, and then this would be n by m. But here we're going to pull apart only a smaller number than m. So R here is, the point about R is that it's usually going to be much smaller than m. So we're looking to find a set of features that can help you to characterize the data, but is much less than the number of movies. So here we're going to look for categories. Maybe we're going to try to group the movies into categories. That's the general idea behind this. Okay, so the 3 matrices that you get out of this process. Let me go to, I can't go to full screen for this one. Sorry. So the matrix product is going to be A is equal to U multiplied by, sorry about my handwriting, multiplied by this matrix called sigma, Rachel calls it S, times V transpose, and Rachel calls this VH in the notebook. Okay, but this is what they're called in the most people refer to them this way. Okay. I want to, let's see. So these tall skin, this matrix U and V, these are called embedding matrices. And they isolate some kind of representation of the information that you're giving it, and they find hidden features in that data. And the number of hidden features you can specify by R. How many hidden features do you want? And hidden features could be like movie categories, right? So you're going to specify that to be a small number so you can deal with it. Okay, so the first matrix is going to be an M by R matrix, and the columns of this matrix U are orthonormal, which means that when you take a column, the dot product of a column with another column, it will be perpendicular to each other. You'll always get 0. And if you take the dot product of a column with itself, you'll get 1, since orthonormal. It's actually unit orthonormal vectors. Okay, and in the same way, this V matrix, the rows of the V matrix are orthonormal, unit orthonormal vectors. That is, the rows are independent. If you take the dot product of a row with another row, you get 0. If you take the dot product of a row with itself, you get 1 because it's a unit. It's a unit. Each row is a unit vector in V, and each column in U is a unit vector. So that's what makes these two matrices special. What makes this sigma matrix special is it's diagonal. That is, all the entries that are off the diagonal are zeros. Okay, so back to Rachel's work here. This is in the notebook. She's just using linalg from, I think it's coming from scikit-learn to do the matrix decomposition. I'm going to go back now to, well, I'm going to open up this new file called britlet.xls. That's also in the FastAI repository. So let's see if I can find it. Background somewhere.
While Jonathan's bringing that up, linear algebra, of course, is pretty hard topic. Everyone needs to master it, blah, 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 all that. You cannot get away from it, especially when you start to get into advanced machine learning and deep learning. The one course that I will recommend, if you guys can get your hands on it, it is available via Coursera. It's older. It's called Coding the Matrix from Philip Klein at Brown University. Get all his materials, figure out how you can get access to the entire course. It's a few weeks, but that undergrad linear algebra course is perhaps the best out there in terms of actually going through linear algebra. And again, you cannot do this stuff well without mastering linear algebra. Just my not so humble opinion.
Can you post the link or the name again on the Slack, please?
Absolutely.
Yeah.
Absolutely.
Coding the matrix. I guess, can you put that in the chat? Then everybody can get it.
I'll put it on both.
Okay.
Let's continue.
Great. Let's see now. Clear,
Thanks.
I want to clear my drawings. There. Okay, so this is the spreadsheet that Rachel included. It's called britlet.xls, and it's a really nice example of it starts with the term document matrix from British literature. So instead of Netflix users and movies as your rows and columns, it has books as the rows and words that occur frequently in the books as the columns. And in this case, there's a lot of names, as you can see, but it's not only names. Said, quote, Phineas, there's a lot of names and so on. So, so the idea would be to try to group the British literature into different genres by pulling apart this book term. They call it a term document matrix. By pulling apart this term document matrix into the product of the two matrices. So the documents are the books, and the terms are the words, or the tokens, right? And so she has the term document matrix, and then she has let's see what she said in the intro. Okay, so I think she gives you information about how you can reproduce this about the Python notebook that she used to make it. But so we see the term document matrix, then we see the SVD method of pulling it apart, and we also see the NMF method of pulling it apart. So since we talked about non-negative matrix factorization first, let's look at that one first. So the two matrices are called matrix W, and generally they're called matrix W and matrix, I forget what the other one is. If I could, sorry, I'm trying to find, there's the other, there it is, matrix H. So matrix W is, it doesn't give the dimensions, but it's the number of books, the number of rows are the number of books, and the number of, she has this arranged as topics. She chose to break this down into 10 categories. That's a hyperparameter that you can choose yourself. You can do 3, or you can do 40, or you can do 10. It's up to you how many categories you want to look for. And so the H matrix, remember, since W times H has to be equal to the term document matrix, the number of columns in W, which is 10 columns, has to be the number of rows in H, so that when they multiply together, they can give you the right dimensions back. So this is actually what it looks like, and W times H gives you back, and these are the labels for the rows, the labels for the clear. It shows you the entries in these matrices, and these are actually not already numbers, but the term document matrix, yeah, there are already numbers in there too. So you would want to compare the term document matrix to the product of W times H and verify for yourself and that it's close. And that's what it's supposed to do. And then as an exercise later on, we do that, I think, in the notebook. So that's the NMF method. Then the SVD method is pulling the matrix apart into three parts: the V, the S, and the U. Sorry, the U, the S, and the V. And so here's the original term document matrix. No, this isn't the original. This is the U that you get from the singular value decomposition. Now remember, singular value decomposition is essentially, for us right now, it's just magic. You give it the matrix, and out comes out comes U, S, and V. So, and this is the U that came out. You told it you wanted 10. You told it you wanted R equals 10, the number of topics. That would be R in our discussion of singular value decomposition. So you tell it you want 10 topics, and so it pulls it apart. It pulls that term document matrix apart into a U, which has, remember, it's U, the dimensions of U are M, the number of books, by R, which are the number of topics that we wanted. S, remember, is R by R. So back to is everybody seeing this spreadsheet? I'm proceeding by thinking that everybody is seeing this. Is that correct?
Yes.
Okay, great. I could be talking for 10 minutes to myself, and I don't know if you're seeing the same thing. Yeah, so here's the diagonal matrix, the S matrix that it pulled out. And it's notice that it arranged the results so that it's sorted by the size of these entries here. And these are called the singular values. That's just what they're called. And it's sorted from large to small. And then this is the V matrix. Remember, the V matrix has an R, it's R by N. So R is the number of topics that you chose, which is 10, and N is the number of terms, which goes to, I don't know, 26,000 or something. I don't know how many. Oh, we've limited it to a smaller number. I think 60, I think, right? So these three matrices now should multiply together to give us the original matrix. And I think in and this is an exact reconstruction. So it's not approximate. They actually, oh no, it is approximate because, so I was saying that if you do the full decomposition, then it's exact or very, very, very close. But since we've asked it only for the to use 10 entries in the S matrix, it's going to be an approximate reconstruction, but it can be very close. Okay, so now let's go to the notebook and see how this is done. Let's see, to find that. Here we go. Okay, back up to, okay, that's after the discussion of lemmatization. We've just done matrix multiplication. This is the SVD. Okay, so now here's where you do the SVD in using scikit-learn. And vectors is what comes out of, I should tell you, vectors is the input to this. And so linalg.svd is a package that comes from scikit-learn, and it does the singular value decomposition for you. So the output, you want them to be named US, and I don't know why Rachel has this name VH, but that's what she wants to call it. So you give it what you want the output to be called. You're calling this function from scikit-learn. The input comes from the count vectorizer up above, and you specify full matrices equals false, which means that you don't want to use the full decomposition. You just want to use a subset. And I don't see right now where we chose 10. Maybe that's a default. Let's see, S. No, I guess we didn't. I guess full matrices equals false, but it decided that it wanted 2000. Let's see, why? So the number of words in the, I think we've gotten away from the Britlit thing to a more general one. The vocabulary in the first database that we were using, there's 26,000 words. And let's see, this is the number of news, which data set? It's confusing because we're jumping around from one data set to another. The 2034, I think, has something to do with news, news groups or something. Anyway, here we didn't have a chance to tell it how many, what the dimension of the S matrix is. So I'm a little bit wondering about that. But then she asks to confirm that we have a correct decomposition. So to do that, you can use the all close function, where it has default tolerances, and you can ask it to verify that the original the original matrix is indeed the product of the three matrices that we pulled out of the singular value decomposition. So that, just to demonstrate for yourself that it does work. And the other thing that we claim when we have singular value decomposition is that the U and the VH are, each matrix is orthonormal, which means that its own columns are orthonormal, and for VH, its own rows are orthonormal. So a better way to say this, I don't want to be thought that U and VH are orthonormal to each other. So I should say it this way, each of U and VH are orthonormal. So remember what this means. It means that the columns of V are orthonormal to each other. That means when you take the dot product of the column with a column, you get 0, except if the column is itself, then you get 1. So that's what it means. And you can verify it this way. Define an identity matrix by just using this I function from NumPy, and I just tell it the length of the identity matrix, the dimension of it. That's what this is, and I get an identity matrix. And then I can assert that that the transpose, that U transpose U, that's the column multiplied by itself. Sorry, that's the transpose of the matrix multiplied by the matrix itself. And I should end up with the identity matrix. That proves that if that's true, that proves that all the columns are orthonormal. And then you can do the same thing with the rows of VH. In this case, we want VH times VH transpose. That's a way of testing whether the rows are orthogonal to each other. And so when you do this assert function and you get no result, that means that it's true. So we can do that, and we get no output from that, which means that it passed the test and they're correct. Okay, and now this is the interesting thing about the singular values. It pulled out 2,034 singular values. Let me go back. It said full equals false, but I don't think it did full equals false, because it gave the whole thing. It gave an R matrix that's the same size as the U matrix. So I'm a little bit confused, because we're supposed to be able to specify how small this is if we want it to be smaller. Actually, it doesn't matter, because what we can do is we can just choose. What we do is we just choose the biggest of these values, the biggest of the singular values. So that's what we're going to do next. We're going to see. When you plot the singular values, remember they're sorted in order. The thing you notice right away is that they drop rapidly. So most of the values are small. And that means that most of them you don't need to reconstruct the matrix. You could go back and reconstruct and almost reconstruct the matrix by ignoring a lot of these. And that's what people do. So this is the first 10 of them. Notice how you can see here, it drops very quickly to maybe, this is, the knee in the curve is about 50, right? If you look at the knee in the curve. And here we're looking at the first 10 values, and they've already dropped to 150. I suppose if you looked at the first maybe 20, you'd probably get to this knee. Let's see what happens if I do this.
Do you think you could remind us again what the actual values represent here? Like what is this plot telling us? You know what I mean?
This plot, well, okay, this is very abstract. So these, but I will have a comment about this later on. These are the entries in that S matrix.
Diagonal, right? Yeah.
Right? And if you're doing, let's say if you're doing a Netflix movies versus users decomposition, the R is the number of these singular values that you keep. And you can see here that you're getting pretty close. Let's see, if I go to, so I'm going to answer your question, but let me just go a little bit more. If I take 30 or 40 of these singular values, I want to see how quickly I can get down to the knee in the curve. Yeah, the knee in the curve is about 50, right? And so you can imagine one idea would just be to keep 50 of them, right? And if you just keep the number of entries that gets you down to the knee in the curve. So if I keep only the top 40, the highest 40 singular values, I am already down to 50. And if you just keep the first 10, you're already down to this 100 and something. This
right.
number,
I guess what I'm asking is, what does that Y value mean for us?
Yeah. So that's a really good question. And what it's telling you is it's telling you, say, if you're breaking down the Netflix user movie database. Sorry, I'm going to ignore that. If you're breaking down the user movie database into 10 categories, then these numbers tell you the affinity of this category of movie with this category of user. Does that make any sense?
I'm not really following.
We're breaking down the movies into 10 different, we're trying to break down the movies into 10 categories, and we're trying to break down the users into 10 categories.
Right.
Okay, if we choose R equals 10. And so the values of the diagonals along the R matrix, suppose we just keep the first 10 of them, they're telling us something about the affinity of that group of movies with that group of users. So we have, let's say, older users, people that are older, maybe senior citizens, and then which what is their affinity towards monster movies or westerns or or space movies, right? That's what these values might represent. Does that make any sense?
So it's like how well you're clustering the documents. Is that kind of?
Yeah, in a term, let's see. Yeah, it's very abstract because we can apply it to Netflix, we can apply it to term document matrix, we can apply it to, image vectors and so on.
Sure.
But it's basically the affinity of one categorization with the other. So terms and documents would be if you were doing the term document matrix.
Right.
Right? Does that make any sense?
Yeah, but sorry, go ahead.
So what Joseph just explained is actually very accurate and apt, but it is important that we all understand that intuition. And if you'll allow me, let me take a slightly different use case example than Netflix. Facial recognition. You take an image, we break down that a two-dimensional image into whatever, into a column vector and so on, right? When you do this matrix multiplication, it's saying of the entire image of a face, identify and say, this is a nose, this is an eye, this is a mouth, and so on. We don't know what those are in an image necessarily, even looking at the pixels flattened out, but you kind of get to, the matrix factorization is take that matrix of the image, split it up into an X times Y, or whatever those matrices, to say this is what one is like think of coefficients. Does that help? Is that helping at all?
Okay, so from an overall standpoint, right?
Mm-hmm.
We have a collection of documents or whatever we're trying to group, and we don't know what the labels are or what the groupings are.
That's right. That's right. You're letting the model do it for you.
Right.
So you're letting your model just say, I've seen that these images and these faces are grouped into these categories, and then a lot of times you can actually identify what features it has actually pulled out. Sometimes you can't, but sometimes you will say, oh yeah, that's facial recognition. You can say, yeah, it's focusing on eyes. It's determined all by itself without input from us that eyes are important.
Right. Okay.
That's the unsupervised learning. That's the unsupervised learning that we're talking about.
Yeah. So just so I understand, right? So like with OMFIT, you have some collection of documents and you want to classify them into categories, but you already have the category labels. And in this case, like we want to maybe try to classify documents without category labels and say, here, we're going to provide 10 labels. We don't know what the labels are, but we want you to just categorize things into 10 different groups, right? And so this graph you were just showing above shows that like if you pick your number of groups to be 1 or 5 or 10 or whatever, this shows you how well those groupings sort of fit. Sorry, those documents sort of fit within 1 group or 5 groups or 10 groups.
Yeah, let's see. I'm trying to see if there is an interpretation here that I'm missing. I'm going to think about this and get back to you on it next time.
In a purely mathematical sense, it says how much of the matrix values, the original matrix, are you capturing. Now, transferring that into either image, how much of the image sensitivity you're capturing or image signatures you're capturing, such as eyes, nose, or how much of the topic affinity you're capturing is harder to do. But in a mathematical sense, it just says the farther down this curve you go, the more of the original matrix values or you're capturing. So
okay, actually that makes sense.
I think it's but isn't it the other way around? The higher you go, the more you're capturing.
Well, no, if you have more topics and more groupings, then you capture more nuance, right?
Oh, of course,
Exactly.
of course, of course. But this is telling you the importances of the different topics. So like topic number 1 is the most important one because it has the highest score here, the highest singular value. It explains a lot of the variance of the data. The second most important and the third most important and so on. And so by going to the 10th, going to 10, you picked the 10 most important topics. And this gives you some kind of a quantitative relationship about how important they are.
That's correct, Joseph. I was just saying the more you go to the right, the more the total value of the matrix that you're capturing.
That was actually super helpful. Thank you, guys.
Yeah, great. Okay. That's right. So yeah, I mean, in the limit, you'd go all the way and take all the singular values, but
exactly, and only then will you capture all of the matrix of the original matrix.
Yeah.
Srinivas, would you call that capture the information in the matrix? Is that the terminology?
Yeah.
In fact, you could reconstruct the
in
matrix.
That's why I said mathematical, because mathematically you're capturing the overall values in the matrix, but then the intuition transfer to whatever it is that you're analyzing is a little bit harder. But
and in order to capture all information, you'd need the same number of, you'd need your R to equal the number of the data set records.
That's right. And then you would actually recover the matrix to machine precision. So it's in that sense, it's exact. Does that make sense? In other words, the USV,
it does make sense.
Them together. You'd get the original matrix to machine precision, so it's more or less exactly captured.
Yes, thank you.
So so this is the facial. I didn't want to go into the facial recognition model because it's more complicated in terms of matrices and so on.
Apologies for
I think it's easier to think. I mean, it's easier to think. I mean, yeah, each image is actually turned into a row vector, column vector. I was starting to explain that, but then I ran back to the Netflix user movie document matrix because that's easier to understand. So let's see. Yeah, so Rachel said or points out that when you factor the matrix breaking either way, either using USV or non-negative matrix factorization, you're breaking down the matrix into some kind of topics or categories or groups, clusters, basically. You're letting mathematical algorithm find those clusters for you. It's unsupervised. And then often when you come back, and this is what Rachel does when she looks at the britlet.xls, she shows that some of these, I forget where she showed these examples, somewhere in the video, I think, and maybe here too. She showed that the topics that it finds make sense. So let's see. Yeah, so she did this with, let me go back to what this is. Is this the original? These are the news groups. Okay, this is the news groups data set, which is postings on news groups. You can look at this one posting here, and it looks like it's about astronomy, but so without a human user to determine what the topic is, you can actually do this non-negative matrix factorization and get that result. So here it is, the non-negative matrix factorization from scikit-learn. I think she defined this up above. Let me. She defined CLF somewhere as the the element from. There it is. This is the element from scikit-learn that performs that non-negative matrix factorization. So it's called. Remember she imported decomposition from scikit-learn. And so decomposition.nmf is this non-negative matrix factorization. And here you specify the number of components that you want. And I'm not sure what this random state equals 1 does. But here's where you can specify that you only want 10 components. In the SVD, let me back up to that for a second. In the SVD, it's sort of manual. You get the full size matrix decomposition, and then you have to just pick the highest. I guess you look at that plot of the singular values and you say, oh, it makes sense for me to only keep 10 of them or 20 of them or whatever. So it's manual in that sense. You have to decide how many you want to keep, and that's how you specify that R. In NMF, you specify that as an input. So here would be 10, you know, if you want to keep 10 components. I think she made it 5, number of topics be 5. And it's interesting, this is kind of, so I wouldn't call it topics at the outset because we don't know, you know, if we're naive and we're just using non-negative matrix factorization for the first time, we may not understand what it does yet. So we would expect it to do some kind of grouping or some kind of clustering. And then after we look at the clusters, we decide, yeah, they must be topics. So that's why she's calling them topics at the outset, and that seems a little bit strange to me. But the thing is that the mathematical technique finds the clusters, and then you can retroactively look at what those clusters are and say, that makes sense. So here, if we look at the topics, if we look at some of the words in each topic, we find that one topic has JPEG, image, GIF file. You can see this has to do with image processing. The second group of words from this topic has to do with, okay, that's email, apparently. And the third group, space launch satellite, NASA satellite, this is a space science or astronomy. And then Jesus, God, people, Matthew, atheism, this is all about religion. So it just jumps out. In other words, you didn't say categorize these things by religion and space and image processing. You just turned it loose and said, find the clusters that make sense. And the mathematical technique did all the work and came back and showed you this. And then retroactively, you can look at it and say, yeah, that makes sense. It has found these clusters that we asked it to find are actually topics of these Usenet posts. Does that make sense? And here it looks like there's some overlap. This one looks like it has image processing and some overlapping terms. This one was some kind of internet terms. So, you know, you can imagine asking it for more topics and then trying to pull apart to try to retroactively look at the data and figure out what these topics that it found were. And if you ask it for a lot of topics, like 20 or something, you won't be able to easily see what each one means. So some of these, they're not necessarily going to be human interpretable. They're only interpretable to the mathematical algorithm. But to me, it's just a wonderful surprise that you told the computer to find the clusters, and when it did, it means something to humans when you look at it. That's what's so amazing about it. I just think these techniques are magic. They're just amazing. So
they're used.
Yeah.
If anybody has use cases or wants to know, I have to be a little careful about sharing this. We use them for one project a couple of years ago. You used physician nurses' notes. These are handwritten notes once they've been transcribed and so on and so forth. The notes are then set to create categories on which you can then categorize your patients. So if the notes would say elderly woman with osteoporosis, they go into the weak old ladies category, or smoker male, they go into the elderly smoker, you know, so and so categories. And then that's how you're able to segment your patient population, as opposed to using other data, because you don't have access to that data about what their gender is, what their date of birth is, and so on.
Thank you. So Marsh, so what you do then is well, this is the same thing we did. We look at the categories, we look at the clusters that it found, and then we human identify them. In other words, the user goes in there and says, yeah, this, I look at all these words and it jumps out at me. It's weak old ladies, right?
Right.
And I look at all these words and this is infants that are at risk or something like that.
Bingo.
So the meaning gets, excuse me, you have to actually say what the meaning, you have to interpret the categories that it found.
Mm-hmm. Yes.
Yeah. So do you have any of those to share, or you say you might be able to share some of that?
No, I can't. Sorry.
Oh, yeah, because it's
Insurance
patient,
company
it's
consulting.
personally
Yeah.
identifiable information. That's the plague of health applications of data science. The data sets are usually proprietary. You don't want to release them because they have personally identifiable information in them, and there are rules about that.
Right. And those are specific to the audience here. Those are specific to the United States and a few other countries.
Yeah.
There are countries such as Taiwan. I had a meeting earlier this week with a researcher from Taiwan. He can get full access, carte blanche, to the entire Taiwanese healthcare data set. Everything.
Yeah, and China too. And so that's why I think that the big progress in medical applications of AI is going to come from China, because they don't have these restrictions and they have huge databases.
Yes,
So,
and China is 3 years, a full 3 years ahead of the United States in AI applications. Let's be realistic.
Wow.
And we
are you talking about across the board or just in NLP?
Across the board.
Really?
What makes you say that?
Facts that I have. I have to work with all different platforms, different use cases, working with Chinese firms and global firms. I have a global role. And so as we look through this and look through what the capabilities are, I mean, even if you go outside of that, just read the news. There's a brilliant PBS Frontline, the US, has a 2-hour Frontline documentary, I think a couple of episodes ago, on artificial intelligence. Just look at that. Just watch that 2-hour documentary. It's on YouTube. It's all freely available. You'll get a very good sense. It's not about they're not advanced in terms of the mathematics or statistics or any of that. A lot of that's coming from the United States. Even the technology has to run on hardware developed in the United States. These are Intel chips and so on. And there are regulations and tariffs to prevent those chips from being used in these systems by Chinese companies, which there are tons of. But of course, those Chinese companies are able to stockpile, were able to stockpile. And so they're using what they already have, the supply they have, to develop in these systems. The point on their 3 years ahead is on actual daily use case applications.
For example, they have, because they're trying to identify and segregate the Uyghurs, the Uyghur population.
Yes.
They've pushed facial recognition to an extreme, and they can look at a crowd of 20,000 people in a single photograph, and they can identify, photographing people in a stadium, they can identify all of them, all the faces, and classify them as whether they're Uyghurs or not.
Yeah, I mean, I don't know if that's the type of ahead we want to be anyway. But.
Exactly. So this I would think is not a moral application of AI, and people have to think about that, although they won't. I mean, people should think about the moral implications of what they're doing, but unfortunately, human nature being what it is, a lot of people are going to say, if I can make money doing this, I'm going to do it, and I don't care about any kind of moral implication. They don't even want to think about it.
That's utterly true. That is utterly true.
Yeah, and there's nothing much we can do about it except to try to set up laws that protect people from being exploited this way.
Or at least don't work on that technology.
Yeah. I mean, you have a choice. You have a choice of whether you want to work on it or not. And a lot of people at Google are exercising that choice and trying to put pressure on the management at the risk of their own jobs to steer the management away from these kind of unethical applications. But I don't think they're successful. I mean, Google used to have a motto, "Don't be evil," and then a few years ago, they just dropped it. Said we don't need to do this anymore. And just a couple weeks ago, the 2 original guys who founded Google are gone. They've left, and so that ethic of "don't be evil" left with them, I think.
Because Sergey and Larry did not feel, exactly to your point, Joseph, Sergey and Larry didn't feel the company it represented those original values, and they had enough. And by the way, they just walk with their money. And they're insanely wealthy.
Yeah. But I think the nice thing is, to me, is that in Silicon Valley, there's a lot of social awareness, and people want to be doing the right thing. And there's a big movement in AI now to keep it ethical, and I think that's encouraging to me.
Yeah, but Silicon Valley is not the be all end all. There are pockets around the planet where people will do this for money, or they're organizationally. When I work in strategy, you can develop the workflows and the development where you can sort of take, everyone works on such a small piece that those ethical frameworks don't necessarily have to apply. Just saying. It's a complicated situation, but everyone.
So that's your divide and conquer.
Divide and conquer, where you divide lower and lower parts so that people don't have personal ethical hits against it, or even organizational. There are ways to weave it all together. So the more people start talking about ethics, the better we'll be. But we don't have enough people who do, and we don't have enough people who even understand the mathematics that go into some of these models.
So I have a quick question then related to this topic. What is the difference between the type of problem that we're aiming to solve with this versus with autoencoders? Like what do autoencoders aim to solve? And is it, so I think Mosh said it was not the same problem, but like what's the difference there?
Well, I can speak to this, and then I'll let Mosh talk about the autoencoders. This method that we're using now is good for recommendation engines. So, you can have movie reviews, you can tell, well, one thing it's good for, let's say not just limited to recommendation engines, but one thing. Amazon uses these kind of techniques too, like products and users. They can tell, that's how they can recommend different products to you when you log in, because they look at users who have similar encoded, these U columns and V columns V rows that we're talking about. These are like encodings, and you can, the products are encoded in some one way to think about this is the products and the users are encoded into higher dimensional vectors, which can pull out a lot of useful features. And then if you compare, if you find a bunch of users who like this product, and then you find another bunch of users who are similar to them, then you can be almost sure that they'll also like the product. And so then you can recommend the product to them. Now, somebody asked on the forum a question about this in the context of the Netflix movie and users database. And it was a really good question. So when you look at that, let me go back to that for a sec. I don't want to be too long-winded about this, but I'm going to go to one document where, the one slide where I had the user movie, and I'm trying to figure out what I did with that. Let's see very quickly. This is not it.
As Joseph brings that up, just the point on autoencoders. Autoencoders have more to do with neural networks and the way neural networks is structured. What we've been talking about with matrix factorization, that is still more in the statistical realm where, it's normal human statistics that we can understand. And we're doing a lot of linear algebra, trying to keep it within that space. There is, it's neural networks just introduces a lot more of a probabilistic mindset, and you sort of like let yourself go. I know.
But I mean, in terms of the problem you're trying to solve, like,
yeah.
Is it the same type of, are you?
Yeah. In a sense, you're simplifying by either reducing the number of features that you focus on, and so on and so forth. You've all seen, like, in image recognition with neural networks, the neural networks don't look at the entire image, 100% of it. It'll look at certain bounded shaded areas, right? Certain areas that it feels have a higher concentration of distinguishing features. And so that's what autoencoders try to do so in a sense, you're kind of doing the same thing. It's just the way the mathematics for it are completely different.
Sure, yeah. Outside the mathematical realm, though, are you still like basically clustering your data set with autoencoders?
I feel like I don't know enough to be able to say something that simple.
I think it's all about dimensionality reduction.
It is yeah.
Both techniques are using dimensionality reduction to reduce a large number of items into a smaller, groups into a smaller number of categories.
Right.
And so the point that I wanted to make about this Netflix thing, return to this, is if you look at, can you see this Netflix matrix here?
Yep.
Users and movies. Okay, so if you look at this, each user is defined by a vector of length 4 in this case. Of course, the real case would be like vector of length 20,000, whatever. But the vector of length 4 is how you specify a user. Each user has its own unique vector of length 4. But now if you break this down into 10, let's say you break it down into, you say, let's turn loose this matrix factorization and find 10 groupings. We'll call them groupings at the outset. And then later on, we can look at them and see that, yeah, indeed, they are categories they are genres of movies. That's what happens when you look at that. But at first, you'll say, let's break this into clusters of 10 different kind of groupings. And then, so then what happens is each user, you get this W matrix where each user now has a vector of length 10, is represented by a vector of length 10. And it's a much richer representation because those vectors can have real values. So there's like infinite numbers of, you're spanning a very large space. Whereas here, you're restricting it to movie ratings, and so everything has to be integers. So can you see that when you do this embedding of the user into a larger space, you're going for a much richer representation than you can have if you just take this vector by itself. And again, somebody asked the question, what happens if you go through this Netflix reduction and you find all of your embeddings, your embedding vectors, like in the W matrix and the H matrix, whatever. But what if you have a new user and you don't know anything about, and all you know about this user is his or her likes and dislikes of these movies, the ratings. You don't know their embedding yet. And so what can you say about this user? Well, you can say something about this user because you can look for other users who have a similar representation in this more primitive space. And you can say, well, this user is likely to have the same representation in the higher dimensional space too. And so you can make estimates of what this user's embedding would be. Does that make any sense? In other words, I'm talking about a user who is not in the original Netflix database. So, and we want to be able to predict something about his or her dislikes and likes. And what I'm saying is that you don't have the embedding, the rich 10-dimensional embedding. You have that for all the users who were originally in the Netflix database, right? Because when you break it down into the matrix factorization, then you get this 10-dimensional vector for each user, right? But what about a new user who wasn't part of this matrix before? All you know about this new user is these kind of numbers, right?
Why not just run the embedding again?
Well, you could, but that's huge. I mean, that is a huge amount of compute, and nobody's going to run the whole thing again just to get the ratings for one, just to get the embedding vector for a single user. So instead, you compare this user to a lot of other users and find users who are like him or her in this vector, in this primitive representation, in actual users in the database. And then you can then estimate what the new user's embedding vector would look like from other users who are near him, who are who have these kind of vectors that are near him. Does that make any sense?
I think so, yeah. And then it seems like, and I don't know that much about autoencoders, but it seems like if you were to use an autoencoder, then you don't need to worry about it because you just run them through the autoencoder, which doesn't require a massive amount of compute because you don't need the whole data set. You just need the model, and then boom, you can see what their embedding is.
Mm-hmm. Yep, that's exactly what people say. And part of the reason why people just sort of default to using the neural networks autoencoders because they don't have to do all the data pre-processing. You just throw the data at it and it automagically happens.
Yeah, I like that word.
So, but how expensive is it actually in terms of compute time to run these techniques we're talking about today?
For professional
Well,
companies,
there's an in the notebook, she actually does some, she actually shows us some of that.
Like, I didn't know if it would take a long time if you get a new user, if it's like, okay, well, I've automated the notebook essentially. Like, how long does it take to run? I don't know. That's my question.
how much
Well,
data
think
do you
about
have?
it, the Netflix database is going to have millions of rows and tens of thousands of columns. So that's a significant computation.
Got it.
And maybe even beyond what you can do on a laptop or something. You know?
Right.
So I think she has a couple of interesting timing comparisons here. She does this USV decomposition, the SVD, using this linalg.svd. I think that comes from scikit-learn. And it takes, on my computer, it takes 9 seconds. Then she used, this is NumPy. This is just NumPy, the native function from NumPy. 9 seconds. If you take from, I'm not sure where that's from. Anyway, if you take this decomposition from sklearn, you get 4.38. Yeah, I think this is native to NumPy. This is just from NumPy. You don't have to even import anything, and you get this 9 seconds. But then if you use this decomposition function from scikit-learn, the randomized SVD, which Rachel talks about, you can cut that in half. And then if you use Facebook's new version of randomized SVD, you can cut it down to 1.63 seconds. Yeah, and I don't remember what the size of vectors. Remember, vectors is 10,000 by 26,000 by 2,000, right? So that it costs you a second using the state-of-the-art method, which is Facebook's. It costs you 2 seconds to break that down. And remember, we're talking about millions instead of millions of lines instead of 26,000, and we're talking about tens of thousands of columns instead of 2,000. So that gives you an idea of the scale.
Yeah.
And
so
yeah.
How do you compare the quality of different techniques in this area? Like if I want to, cluster into groups of 10 or groups of 20 or whatever, and I want to use an autoencoder versus, these methods, like how do I compare the quality of the clustering? Does that make sense?
Yeah, all you do is follow the standard research methods. Same inputs, same data set, and compare them. That's it.
No, but I mean the outputs. There's no labels, right? So like, how do you measure the quality differences?
Well, one thing you can do is do the Frobenius norm of the matrix. Like, in other words, you take the matrix that you're trying to reconstruct, and subtract from it the estimated reconstruction from your matrix factorization technique. You subtract the matrix, the estimated matrix from the original matrix, right? And you would expect that to be small, and you can make it quantitative by calculating the Frobenius norm, which is just basically the sum of, so when you subtract those two matrices, you get the differences, right? And those differences should be small. To quantify that, you then add up the sum of the squares of all the differences in that, and then that's the Frobenius norm. And so one way of quantifying how well you did is just to see how small did you get the Frobenius norm.
Isn't it context?
Matrix, pardon?
Application dependent. So if you're using the content recommendation, then surely you will have like some user-based metric that you're trying to optimize against, in which case you would use A/B testing if you had the scale.
Mm-hmm.
So I think it's just depends on the actual application.
I don't know I can't see how you could use A/B testing for anything where you'd be clustering things, but.
Well, if you think about you doing content recommendation, say you were Netflix and you had a range of different methods and so on, and you know that basically you have like some user metrics that you're optimizing for on the user interface and the actual engagement metrics, then you would, when it comes down to it, it's like something like viewing time. If you're not, put it this way, if B cut down the amount of viewing time in that group, you wouldn't choose it, would you?
Yeah, it seems, yeah, maybe. It seems like so far removed from, yeah, I guess it could work. I'm not sure.
Two different things here. One is you're saying predict something, and the other one is more of an operations workflow. You're building recommendation engines and you're going to work it in. And so which ones do you pick for a certain group of users and so on? That's why you do the A/B testing, and it just sort of blends in. Look at Facebook. My meetings with Facebook, they've said to me, every single Facebook user at any given time, this was about a year ago, is taking part in over 60 A/B tests. They don't know it. And this is on average every single Facebook user. And so you're always going to have that as part of the operational workflows. When I did search, we had, every user was always part of several different A/B tests. They just didn't know that they were, but they were part of it. The other part is, do you predict something? Do you build a prediction and take that prediction engine and use that sort of prescriptively into a whole new operational workflow? So it's how you use and apply these methods and frameworks. I hope that helps. Or
yeah,
There's one. This is Darren. There's one other thing. I don't know if this helps. Cohesion. You can do cohesion measures. I know there's one built into the LDA with Jensen, but like you would do if you were doing clustering. Cohesion measure.
Hi, this is Philip. Just to add to the confusion here, I think CSRF's points go a little bit into the direction, and this is something that I've asked myself for quite some time now, is that with all these nice clustering methods and so on, there is a sense of subjectivity in it, in the sense that you don't, in supervised learning, of course, you have a label, you can test it, you can pretty much have very excellent tests on that. But with clustering, it's always kind of voodoo to me, because let's assume you're sitting there with a marketing person and they want to do market segmentation. Okay, there's always this user experience, or this expertise goes into this, that someone from marketing knows that there are three groups that you want to cluster into, but this number you essentially have to ask the expert, and that's actually a big critique point of mine, and maybe someone can. I think the question goes into the direction: how can we actually evaluate the quality of clustering algorithms? Now, I know there are some metrics.
You can. So this is a really good point. You actually can, because you can devise your own metrics. For example, you could take the variance of the cloud. In other words, you have these vectors, these embedding vectors that are clustered. You can actually say, okay, in this cluster, I want to calculate the variance of these vectors. How much variance is there? How much, and that's quantifiable. So you can do that for each cluster and decide whether it's a tight cluster or whether it's not a tight cluster. And then you can also ask yourself, where are the errors? Are there members that are assigned to one cluster that are actually closer to another cluster, or that are not closer to another cluster, but that are overlapping in another cluster? So you could ask yourself, you could quantify it like that. Because the idea is to have.
Isn't it possible? Oh, sorry, go ahead. Sorry, go ahead. Yeah, I apologize for interrupting. Go ahead.
No, go ahead.
Isn't it possible that you have like tight clusters, but some of the things in the cluster are misclassified anyway?
That's what I was saying. That's my second point. Is that?
Oh, okay. Sorry.
Yeah. So there's two things you want to look at. One is the tightness of the clusters, and two is how many objects in that cluster are actually overlapping from another cluster. How many objects that aren't really well classified. So that's to your point of misclassifications. And these things can be quantified, although for the second one, you might need some human intervention to test that. In other words, if you say, okay, this is a cluster of sick little old ladies, and then you do some work on it and find that it mistakenly included some 5-year-old children in it, then there's an error there. But the clusters themselves, the names for them are subjective. You have to look at them and decide, like, what did I get? What did the computer actually do for me? What did it actually identify? And that's a bit subjective.
The most junior person on the work team will be assigned to start looking at all those clusters, plot them out, plot out all the characteristics, and say, did we get the clusters right? And it's a manual process. This is where you're using any dashboard tool, Tableau, Power BI, whatever, or just R, Python, whatever visualization tool. Start visualizing, plotting them out, manually check if the clusters are right.
Yep.
Because if there's a lot of money involved in these sorts of engagements, projects, initiatives, you cannot afford to be wrong. You can't mechanize and automate every workflow. It is done manually. It is still, and there is no way around it.
Yeah, thanks, Joseph and Mesh. Your points actually made a lot of sense
so
to me.
For
Yeah,
all your comments and everything. I think
that is super helpful.
The bottom line is that this is really magical. The computer actually finds these clusters that have meaning to us. Some of the clusters it finds don't have. They're only understood by the computer, but other clusters are humanly interpretable, and that's what's so surprising.
There's just to throw in one other, I don't know how much this helps, but another way to measure, like if you're doing a sort of hyperparameters and producing like 100 models or 50 models for LSI or SVD, whatever your topic model, and you're producing like multiple models just to try to figure out how many topics are best and that sort of thing, and maybe other things about your vocabulary pruning. If you do that, one measure I found that's somewhat useful is you do related documents within that produced vector space. And so if your document number one result for your document is itself, or maybe the second one, that you're getting pretty good related document results out of it. And so you can just do a graph, and that way you can identify at least the models, your topic model vector spaces that are just not coherent, because they just don't return some of what you'd expect in terms of So that's an automated way of pruning down your models before you have all those people review them.
Okay, I think this is where we should leave, because we should cut it off because people need to get to a 10 o'clock meeting, and so I was only supposed to go for an hour and a half anyway. So, but thank you all for being here, and I think we covered most of what we wanted to cover today, except for the term frequency, inverse document frequency, and we'll get that next time.